Now we will write down the differential equation, okay, for this circuit. We will write the very simple differential equation. So we have seen that there is a voltage source and there is a RF, LF and a grid. So we can write VAN is RF IAG plus L di dt plus VAG, okay. So very simple equation there, and for the 3 phases. So we can write this equation in a slightly different format, like diAG dt as something like this. So this format of the equation, where you have the rate of change of the variable on the left side, this is used for during the dynamic modeling, okay, of the VSC. We will keep this in mind. We will not use right now, but we will keep this in mind. We will use this in the dynamic model. We will come back to this equation. However, this equation is also useful when we make a simulation block with this VSC. So let us see how we make the blocks in simulation with this equation. So as I told you, so we have this equation here. How can we implement it in for example MATLAB or any other software? So what do we do here is something like, you see, first we get VAN. So this is a VAN here, okay. As I told you, we have just now elaborately discussed how do we get VAN from the switches and the VDC voltage, okay. So you have got VAN, VBN and VCN. Now this is the VAN comes here, okay. So I take the first term in the equation, then I subtract VAG from there. I have subtracted VAG from a block of plus, minus and minus, and I am also subtracting RF times IAG. See, this is the gain RF, and I am subtracting RF from IAG. Suppose I have obtained IAG here. Let us assume that I have got it, okay. Let us assume if I have got this IAG, then here comes the RF IAG, and this I will then put it here, okay. So this is the point where this part of the, say this is, suppose I give 1, here is what I get 1 here, okay, and then I multiply by 1 by LF, and then I get this expression di by dt. So here comes the diAG by dt, okay. So I get diAG by dt here, then I integrate it. When I integrate this diAGT, then I get the IAG back here, and this IAG I will feed it back here and complete the loop, okay. So therefore this is the way I can actually model the whole equation, and by putting different values of SA, SB, SC through this model, I will be able to get IAG, IBG and ICG. Of course, I need to know what is the value of VAG, VBG and VCG, but this model here can show me that, okay, if I give certain values of SA, SB, SC, combination of SA, SB, SC, and if I know VAG, VBG and VCG, I will be able to calculate in this simulation block. I will be able to calculate IAG and similarly IBG and ICG, okay. So this is how we model the whole converter and the differential equation that we have shown. Of course, now we are talking about steady state, okay. So the equation in differential equation format is like this, okay. VAN is this one, but at steady state then we can write this equation on a per phase basis, assuming all quantities are sinusoidal. Then we write this equation, okay. These are phasors, okay. So we write the phasor equations. So L di dt becomes j omega LF IAG at steady state. So these are all phasor quantities. So here I write phasor. Okay. So VAN is RF IAG plus j omega LF IAG plus VAG, right. So therefore this is a very known phasor to all of us. We have studied this in basic electrical engineering, and then we can draw the phasor diagram very conveniently. We assume that there is a VAG voltage and there is a current IAG which is lagging the voltage. So the grid voltage is taken as the reference and the grid current is lagging by phi angle. So IA RF comes here in phase with IA, and j omega is the rotating operator. So j omega LF IAG will take me 90 degrees, and then I will come to know what is the required value of VAN, which is to be produced by the converter. Okay. So the converter has to produce a voltage which is, in this particular phasor diagram, the converter has to produce a voltage which is leading the grid voltage, and its magnitude is more than the magnitude of the grid voltage. We can understand it from the phasor diagram at this condition where IAG is lagging. Now suppose there is a converter where now we want to change the active and reactive power. Okay, we want to adjust the amount of active and reactive power from the converter into the grid. We see how can we adjust active and reactive power by observing this phasor diagram. Okay. So for example, in this diagram, okay, we are keeping the active power constant from the voltage source converter, but the reactive power supplied by the voltage source converter is changing. How can we do that? Here you see that we are drawing two phasor diagrams, one with an IAG1 corresponding, so the grid voltage is VAG same as before, and then you have RF IAG1, and then you have VAN1. So for this condition of IAG1, the voltage source converter produces a voltage which is denoted by VAN1. Now you can also do IAG, you can change IAG1 to IAG2, and therefore you can draw this phasor diagram IF RAG2 plus j omega LF. So then the voltage source converter is basically producing this VAN2. So these are the two voltages produced by the voltage source converter. But what is happening with respect to the grid current? Here you see that what I have done, I am keeping the projection of IA, this projection of IA on the x axis or on the VAG axis to be same under both these conditions. What does this mean? It means that the VAG into IA into cos phi is constant. So which means that the active power delivered by the voltage source converter remains same for both IAG1 and IAG2. Okay, for both these currents, the active power delivered by the voltage source converter to the grid remains same. But what happens is the reactive power, okay, the reactive power, if you see, these are the two reactive powers, okay, Q1 and Q2. This is because of the out of phase component of current, or quadrature, not out of phase, the quadrature component of current with respect to the voltage, okay, VAG. This is changing the reactive power. Okay. So what we have done by shifting the VAN to VBN, what we have done, we have basically kept the active power constant into the grid, but we have changed the reactive power supplied by the voltage source converter from into the grid. That is what we have done by moving the phasor VAN1 to VAN2. Okay. And secondly, we have also changed the magnitude of the current. This is also to be understood. Not only we have changed the reactive power, but here the IAG2, the magnitude of IAG2 is more than the magnitude of IAG1. Okay, this also we have done. So therefore, what we see that by controlling the VAN voltage, that is by controlling the converter's output voltage and moving it, not only by controlling means changing the magnitude as well as angle of this voltage source, moving it from the initial position to the final position, we have kept the active power same, we have changed the reactive power, and we have changed the current flowing from the converter into the grid. Okay. So this is possible by adjusting the controllable voltage source, because the voltage source converter is a controllable voltage source. So I can place it as per my wish. I can lag it, I can lead it, I can increase the magnitude of to the extent which is possible by the converter. Okay. So this is what is meant here. So when do we use this, for example? So suppose this is one example is, suppose VSC is connected, the voltage source converter on the DC bus is connected to a PV source, okay, and the PV power is constant, okay, but now you are asking the voltage source converter to support the grid in terms of the reactive power, okay. So the active power is constant, but the grid is demanding a reactive power which is changing with time. Sometimes the grid is asking for a less reactive power, sometimes it is asking for more. So under that condition, we will control the voltage source converter in a fashion which I have just explained to you. So active power remains constant, reactive power changes. Okay. So in a similar way, I can also draw a phasor diagram in which we are able to exchange a constant reactive power, but the active power will change, and the phasor diagram is shown here. You can see here that this IAG, this is the initial current, and correspondingly this is the VAN1, and then IAG2 will produce a VAN. For IAG2 we have to produce a VAN2. But here you see that the projection of IA onto the x axis, that is corresponding to the Q, that remains constant, whereas the projection on the x axis, so this is P1 and this is P2. So the active power is changed, but the reactive power remains the same. Okay, so when can we have this for the same PV converter? It can happen when the irradiance from the sun is changing. So the power output from the PV converter is changing, and so the P will change, but we may ask the converter to produce the same Q as before. Okay. Of course, you can have both changing P and changing Q, and accordingly the VAN voltage will be adjusted with respect to the grid. Okay. So we can write the active power flowing into the grid as something like this. PAG is the VAG into IAG star, and if you substitute this, then I can substitute the value of VAG as something like this, and when you simplify this, you will see that the power produced by the converter is the power which is fed to the grid plus IAG square RF, the loss component in the filter resistance. Okay. So we have assumed this convention that the PA converter, if it is greater than 0, then the converter is delivering the active power. This is our convention which we will follow. Again, reactive power flowing into the grid, QAG, is nothing but imaginary part of VI star. Okay. And so the QA converter is, if you substitute these values of VAG, this substitute with this value here, then you will get QA converter is QA grid plus I square omega LF. So whatever the reactive power is supplied by the converter, some part of it is absorbed by the inductor and the rest part is delivered to the grid. Of course, these are per phase quantities, and for a three phase system, this is to be multiplied by 3. Now, so therefore, so we can see that this voltage source converter can act as a controllable voltage source, and it can place the current with respect to the grid voltage. The grid current can be placed in the 4 quadrants, okay, which is very similar to how a synchronous machine behaves with the infinite bus bar, very similar. So, this basically it all comes from the circuit law, 2 voltage sources connected by a Rx or an impedance in between, and you can change the power flow. Okay. So, this is the VAG, and you have put the IAG here. So, VI star means IAG star here, and this will give you a positive P and positive Q. So, the convention that we have followed, which is usually adopted, is that the lagging current means that positive reactive power. Okay. So, this is the standard convention which people follow, and so IAG star here and P and Q are positive. Okay. And similarly, here also VAG IAG is something like this. So, IAG star comes here, and which immediately says that P is negative and Q is positive. Okay. So, this is how we can draw the phasor diagram in all the 4 quadrants. Okay. Now, this phasor diagram can only be drawn, remember, now there is a note here, I will note it, that we will explain it, that this is only possible if the VSC is connected to a DC source, I mean a battery or something like that, or a DC source. Okay, we will explain this. So, this is it's not a DC source, I should not use the word DC source, I mean it should be a battery or something like a DC source which can absorb power. It can give power as well as it can absorb power. Okay. So, this is the phasor diagram which is possible. So, let us see. Yeah. So, this is what I wanted to convey here. Okay. So, the VSC is essentially a 4 quadrant converter which can deliver or absorb power from the grid. Okay. So, we can see here that we can place the converter voltage output from the converter, we can place with respect to VAG, we can place it here, we can place it here, we can place it greater in magnitude, lesser in magnitude, less like a synchronous machine connected to the infinite bus bar. You have a E, that is the back EMF, and you have a V, which is the infinite bus bar voltage, and E and V can be, one can be leading or lagging, and E can be greater in magnitude or lesser in magnitude compared to V, and accordingly you will move in the 4 quadrants of the PQ diagram. Exactly like that, the voltage source converter is nothing like that at steady state. Okay. But here is an important point, power can be negative provided the DC bus has the capacity to absorb the power. Okay. So, here we have to be careful that, see, when you connect a VSC, there are 2 possibilities. One is that you connect a VSC which are rectifier, okay, and then you have this L filter, and then you have the grid. This is one possibility. The second possibility is that you have a DC source, a battery for example, or some form of a DC source, and then you have the VSC, then you have the filter, and then you have the grid. Now when you say that the power is negative, what do you mean? You mean that power is positive means power is flowing from this side to this side. Power is negative means power is flowing backward. So when the power is going backward, in case of option 2, there is no problem, because this battery up to its capacity can absorb the active power. Okay, it will be used in charging up the battery. But when the power is negative, okay, when the power is negative from the VSC and it flows into a capacitor, what will happen? Now the diode rectifier will not allow the power to flow back. Okay, it is an unidirectional device. Okay, so this diode rectifier, since it does not allow the power to flow, what will happen? This capacitor here, the voltage will go on rising. Okay, it will go on rising because the active power which is fed from the grid is now being stored into the capacitor and in the form of half CV square, and so therefore that voltage of the capacitor will go on rising. It will go on uncontrollably rising if you go on injecting power. Okay, so in fact to protect capacitors under certain conditions like this, we actually put a bleeding resistance. Often we put a bleeder resistance here, because if the voltage becomes too high, then we just dissipate that energy into a resistance, okay, into a bleeder resistance. Now, but the important point here is that the power flow from the grid or even motor, so this is not grid alone. Suppose there is a motor here, okay, this is the point which I have said here in point number 5, we can discuss it right now, that if it is a motor load, okay, if it is a motor load and the motor has started regenerating, we often run the motor, sometimes we run it in the motoring mode most of the times, but sometimes we run it in the regeneration mode. So then we allow the inertia of the motor not to be wasted, and we put that energy back into the battery or back into the DC bus. Okay, but suppose you have a motor here and the motor is regenerating, so you are putting the energy back and it will get pumped into the capacitor, and the capacitor does not have the capacity to feed the energy back to the source. This is the source here. Okay, here is the source. So it will not be able to do because of the diode bridge rectifier. We will see a solution for this in the next slide. If you replace the diode bridge rectifier, you will see a solution here. But you understand that power can be negative from the VSC provided that the DC bus has the capacity to absorb the power. This capacity is present in the battery. Okay, battery can absorb the active power, but a capacitor does not have. Capacitor also has it, but for a transient duration, not for a long duration. Okay. Okay. So basically we also see the point number 4, that the VSC is a power amplifier. Basically it amplifies the voltage and current, so whatever reference you give, it amplifies it, and it will now so basically the VSC is a controllable voltage source, right? So whatever reference you give, it will reproduce it, but with a larger magnitude at the power level. So it's a power amplifier. Okay, this is an important point. So, but yeah, so it's a limitation. The VSC has a limitation on the maximum output voltage and maximum output current, which means that the voltage source converter from its design or from the way it is built, it has this maximum output current. Okay, you have the I rated, you may have some I transient rating for certain small duration, but normally we keep it as I rated. So you have an I rated and you have a V rated, that is the voltage that can be produced, or it is which is dependent again on the blocking voltage of the devices. So the voltage source converter has a maximum output voltage and maximum output current. Okay, so within that you can set or you can find it out yourself how much is the maximum power that can be delivered by the VSC. So the VSC is always defined in terms of voltage and current usually. Okay, so then you say that okay, this is the maximum apparent power that the VSC can deliver. Okay, it's the S of the VSC. So you can change the P and Q, you can adjust within your limits. Okay. So the maximum apparent power that the VSC can be denoted. Okay. So the last slide I talked about the diode rectifier having this problem that it cannot feed back the energy into the source and the capacitor voltage will go up. So here you see, to get rid of that problem, here we see that we are using two VSCs. Okay, so these are all say made up of switching devices, VSC1 and VSC2. So this is a bidirectional converter. Okay, so the bidirectional converter, so here on this side you have the grid, there is a DC bus and there is a motor. Okay, now this is also called the back-to-back VSC because the active and reactive power can flow seamlessly from left to right or right to left, okay, at different frequencies. So this is say 50 Hertz, this can be 25 Hertz, but it can also be 50 Hertz also. So it can flow seamlessly. So then we use this VSC1 and VSC2. So what is the basic principal operation of this? VSC2, this is used exclusively for motor control, okay, because it feeds the motor. So this is exclusively used for that purpose. So VSC2 always looks into the motor. For example, you can have vector control on the motor or you can have V by F control, and this VSC is used only for that purpose. What does VSC1 do? Okay, VSC1, it exchanges P and Q from the grid. Okay, and how does it know that how much P or Q I need to inject? Remember, the motor, suppose it is a motor, motor is absorbing P. Okay, so what will happen if I see the DC bus, if I don't have VSC1, suppose I don't have the VSC1 and I take power into the motor with the help of VSC2, what will happen? This capacitor will give the power and the capacitor will lose its energy. Okay, so the DC bus of the capacitor will fall. So suppose now we have VSC1. So what VSC1 can know that how much power I need to give to VSC2, okay, is by monitoring the DC bus. If it just monitors the DC bus, it will know that how much active power it needs to send to VSC2. Remember, VSC1 and VSC2, they don't know each other. Okay, so they are not talking with each other, they are not communicating with each other, but they will know how much. So VSC2 only sees the motor and is exclusively used for the motor control. VSC1 knows how much power VSC2 requires by sensing this voltage, the DC bus voltage. If the DC bus is falling, that means the VSC2 is taking more active power from the capacitor bank. So VSC1 will then adjust the voltage here, this voltage, this is the voltage which VSC1 can adjust, and it will then position this voltage VSC1, it will change its position and the magnitude so that the active power is now drawn more from the grid. Okay, so by monitoring the DC bus, the active power from the grid can be changed by VSC1. Again, the other condition is, suppose P is falling, suppose the DC bus is falling, or suppose the DC bus is increasing, then VSC1 will know that we have to reduce the active power. Okay, suppose a condition happens when the motor, suppose we take a condition that the motor is feeding back power into the by VSC2, it is regenerating. What will happen to the DC bus? The DC bus voltage will go on rising. And so what will VSC2 do? It will see that the DC bus is running, DC bus is increasing very fast, at a very fast rate. So suppose the VAG and IA current was something like this previously. Now what VSC2 will do? VSC will make the current like this. Okay, it will reverse the current. So this current, the current which is drawn, this current IA or whatever direction you take, if you reverse the current, how will you reverse the current? You will reverse the current by changing this phasor position with respect to the grid voltage. If you change the position of that phasor, then you will reverse the current. Once you reverse the current, the power will then feed back. So this DC bus which was increasing will now stabilize, okay, by changing the, so this VSC1, it is a very important phasor in this whole system, as long, apart from this DC bus voltage. Okay, so if the DC bus voltage is changing, fluctuating, VSC1 can be controlled or changed so that you can feed power into the grid, or you can absorb power from the grid. Now this was entirely, the discussion was on active power, but the reactive power is something which is energy flow. It's part of the energy flow, but it is not controlled. Here we have not talked about reactive power. So let us take an example. What happens with the reactive power? Suppose this VSC1, okay, VSC1, the voltage of the VSC1, it is such that there is a P and Q. So let me now clear this, all these things. I will erase everything. Okay. So this has become a lot of. So let me talk a little bit about the reactive power. Remember, reactive power is something which is a degree of freedom here. Okay, you see one thing, that the reactive power, suppose let us take a condition where this motor is taking some P and Q. Okay, the motor can take the P and Q, but this VSC, the VSC1 is taking only P and the Q is 0. The Q is 0. When can it happen? If you can make VAG and IA to be in phase. Once you make that one, then the VSC usually, the VSC will take power at unity power factor from the grid. Okay, this is usually the case. We always want the current drawn from the grid is at unity power factor, so that the grid does not have to support any reactive power. Okay, so we make sure that the VSC phasor is such a way that VAG and IA are in phase. Okay, so it's in phase. But here you see the motor is taking some reactive power. So where does the reactive power come from? So this reactive power is nothing but a power, it's an energy exchange which is oscillating through the capacitor. Okay, the source VSC1 does not provide any reactive power, but VSC2 circulates the energy corresponding to this reactive power of the motor through the DC bus here. Okay, but you know, you can make this Q 0, you can make this Q not equal to 0. Okay, you can have another Q. So suppose, so this becomes more interesting, that there is a P from the grid and the P from the motor will match. They have to match, otherwise the DC bus voltage will change. But Q from the grid and Q from the motor may not match. It can be different. As I have just taken an example, that the Q from the grid can be 0, while the motor can take some amount of Q. Okay. So the Q from the grid and the Q from the motor, they are independent quantities, and they can be controlled. So they can appear as an oscillation on the DC bus voltage. Okay, they can appear as an oscillation on the DC bus voltage. Essentially, what I mean to say is that Q is a free variable to control. You can control the Q for achieving certain purposes. Okay, but this is the overall back-to-back VSC arrangement. Okay, where the DC bus and the voltage produced by the two converters VSC1 and VSC2 can manipulate or can control the whole circuit. We will see the control diagram for after we study the dynamic modeling. Remember that VSC2 we have not talked about it, we have only focused on the grid side control, but VSC2 is basically controlling the motor through some vector control or V by F control. We have not talked in details about that because it is actually a whole subject on its own, electrical drives, okay, with vector control or any other control technique. Okay, so it is a subject on its own, so we have not touched upon it, but you can see many of the lectures available from which you can know how to control the motor through a VSC.